hour session and lots of good information coming in the next hour. Before we get started, talk a little bit about the two green pieces of paper on your tables there in front of you. Who is here for the PMTS show? If you could raise your hand. Okay, great. Well, welcome aboard. We've been doing this since Sunday morning. Lots of meetings, in this conference, so I'm not sure if you're familiar with the PMPA Tech Conference is all about, but it's sessions just like this, what we're going to go through here. And we welcome you for participating in this session. So for those of you that are here today, everybody, if you would mind filling out this evaluation once the session is done, the small piece of paper. Then for everyone else that has been at the conference for the last 2.5 days, if you could fill out the overall performance, the large piece of paper before we leave this morning. It really helps the technical committee understand how we can improve, what we can do to make things better for all of us. So, all right, let's get started. This session is called Fundamentals of Feature-Based Quoting. We are pleased to have Ryan Kutz share his expertise with us in this session designed to review the fundamental principles of feature-based quoting. Before we ask Ryan to get started, let's first learn a little more about his background. Ryan is a machine tool programmer and process engineer with Aztalan Engineering out of Lake Mills, Wisconsin. He entered the precision machining industry at the age of 18 after being inspired by a high school shop instructor and the mentality that comes with growing up in an agricultural background. Ryan continued his education at Gateway Technical College in Elkhorn and Racine, Wisconsin, majoring in mechanical design and metrology. Ryan has worked as a process developer and a draftsman and has expertise in Swiss CNC, cam lathes, and has programmed 3-path fixed headstock NC lathes. He has worked for organizations that have served a wide range of industries including defense, automotive, agricultural, aerospace, and medical. With his wide range of expertise, Ryan has vowed to continue his education within the industry, as well as to offer support to the up-and-coming talent by way of offering ideas through PMPA's listserv, as well as to speak at events such as this. Please help me welcome Ryan Kutz and his session, Fundamental Principles of Feature-Based Quoting.
Thank you, Robin. Morning, everyone. Hopefully you all picked up a pamphlet on the way in. I trust you have. Today's session, as Robin mentioned, the fundamentals of feature-based quoting. And perhaps you ask, what is that? Let's take a look. So what is feature-based quoting? Well, there's been some different takes on this, but certainly we see this throughout our shop. We see it in our CAM software. We see it in our metrology methods. We're focused on features, right? And we can simplify our workload that way. Let me explain. So what is feature-based quoting? Well, it's an algorithm-based approach to understanding, applying, and optimizing variability within a contract manufacturer. And I'll add this, while it's true that one may reduce variability through these means, it's more appropriate to term it optimizing. And the reason for that is understanding, just simply by understanding variability, we can minimize it in some sense. So I add some more. In its simplest form, it's a tool, it's a glorified calculator to help reduce the burden that's associated with job quoting. And let me tell you how this came about. I have our estimator, Mikey Welch, here with us, and he can contest to this. We were up last night working on part quotes after the sessions. But we have a large influx of upfront work to do. The reason for that is our low volume, high variety mentality, target markets. We've targeted prototype work to help diversify our markets. And in doing so, you run 10, you run 5, maybe 1 piece at a time. To us, maybe 100 pieces is a big lot size. And of course, with that comes a lot more quoting, right? We don't have these long-running jobs, so we're continually turning over and setting up machines. I'll add this. It is a means to increase the speed and accuracy of job costing in just that, a high variety, low volume environment. And so you say, well, accuracy, that's interesting, right? How does feature-based give us better accuracy? Well, it does this. Through its logic, a set of rules and algorithms, as I mentioned, we can benchmark best practices. And so we can provide consistency in the way that we quote and the way that we manufacture these components. In its most involved form then, it is a total production management system, provided that we can get the feedback we need to accurately adjust this to new principles, to new best practices. It's simple in principle, sure it is. Feature-based quoting is fostered on a simple fact. Even the most complex precision machine products can be simplified by approaching their processes feature by feature. The number of features a part consists of, while tedious, is not what complicates the manufacturing of such a component. Complications and anomalies come from the lack of consistency in the approach taken to manufacture those components. And I believe we can all agree with that. We need to come to some common ground, though, to understand the importance of this method. Enterprise for profit equals competition. Certainly it does. Competition and performance will drive price. Price accuracy is critical to our profit, our bottom line. Reducing overhead costs makes you more competitive in your market. The just-in-time production strategy is effective for gaining market shares also. And reduced product to market time often provides us a portal for price negotiations with the customer. And I say it like this: the early bird has no competition in acquiring that worm, does he? And that's the principle here. A lot of times the job is awarded to the first person to turn the quote around to them, and we want to be that guy. So you say, well, we've got some principles of our own, and we call it lean. We've adopted this. We were transformed by this, and it's worked well for us, so why should we consider something new? Well, when we look in our lean toolbox here, we find standardized work amongst many other things. Today we're going to focus on just that, standardizing our work so that we can understand the best practices to the features of our products. So standardization, explain, Ryan. Sure, I will. The process of developing and implementing technical standards, we know that. To provide commoditization of formerly custom products. What does that mean? Well, it just means what I said, simplifying. We can simplify our products rather than viewing each and every component and reinventing the wheel for every new and highly engineered product we encounter. We can just simply look at it by features. We tap holes. We drill holes, we turn diameters, don't we? We produce lengths, maybe knurls, threads, what have you. And let's understand the best practices and how we do that and apply it to each and every job. Let's understand that variability within our products. And we do this in order we can solve our problems in coordination and consistency. Certainly the manufacturing guys love it, don't they? We give them a plan. We still provide them with their ability to be a craftsman because we're looking for their input to update the way we quote jobs. We want to be on the same page, and this is a problem I've encountered at a lot of shops. They quote a job one way, but yet they don't manufacture it in the method that in the way they quoted it. And so we've looked to just increase our accuracy there. We want accurate quoting. We also want manufacturing to take into account the way we quoted this job, because it was through that means that we were awarded the business. We reduce the time spent engineering and preparing for manufacturing. And while doing this, we benchmark our best practices. We've spoke on that already. But here again, we wanted to look at how much human intervention goes into quoting. What a tedious job. For any of you that have sat and done cycle time studies for a day long, a month long, years possibly, it's a lot of work. Certainly it is. And how frustrated you must be when the guys on the floor completely botch that process that you had, right? Now all of a sudden the cycle time's 10 minutes instead of 2.5 for whatever reasons. And so while we go through today, we need to think of a couple things. As a contract manufacturer, we need to be flexible, don't we? We need to be nimble. We need to be on our toes, ready to respond to whatever customer requirement we encounter, so long as it's a good fit for our business and our machines. And we also want to think logic today, right? Let's put some logic behind what it is, how we make our decisions, how we process jobs. So we'll think feature-orientated logic then. And I asked, what do you process, right? What do your components look like? Certainly maybe like some of ours. Like I said, turn diameters, milled flats, formed surfaces, threaded surfaces, splines, holes, and the list goes on. And think of that now. Now we have somewhat of a new mentality, don't we? We don't have to look at everything as a new engineered product. We can say, that job's got holes on it. It's got a milled flat on it. It's got some cross-drilled holes on it. We do this. We do this every day. So let's focus in on hole making for a while. And certainly we can categorize this into a couple different categories. Axial holes on center, produced by a static tool and the work spindle rotating. Axial holes off center. Perhaps we're indexing a C-axis on a turret lathe and drilling holes with a live spindle. Radial holes on center, right? No need for a Y-axis, just a live tool. We can drill on center. And radial holes off center. And we need to consider then our Y-axis on our mill lathe, right? And that's kind of where this, I need to explain this also. Today's session primarily focuses on a mill turn lathe, right? Because it can provide, in my sense, the most capability, because we can look at milling features, we can look at turn features, and so we understand them both together if we think turn lathe, mill turn. Standardized hole making. Certainly we can do this. And I say, let the orientation, tolerance, and feature size dictate your manufacturing method. Those three then being the only inputs required by the estimator. Standard holes require standard tools. Certainly they do. We've seen that more lately. Quick change systems have provided some of that. I know at Aztalan we have a series of numbered tools. We've assigned a number to the holder and the drill, whatever it be, and it sits in a Lista cabinet in a drawer, and we have that charted. We know what our inventory is, and more on that later. But have a record of this in-house, right? Know what you have. The key to consistent processing can be defined by logical decision making. Sure it can, and we're going to let the logic dictate how we process. That's what we're after today. So here's some considerations for processing logic. And the list goes on. I'll abbreviate this, but cutting tools, what do they include? Well, they include a spot drill, a drill, possibly a boring bar or a reamer to size that hole afterwards. And so we can look at standard drill sizes. Maybe we say, well, in our industry we go from, .032 drills, 032 drills, maybe to 7.5 inch indexable drills. Whatever that range be, whatever's specific to your company, just identify it. And here's another interesting fact. How far do you plan to clear that drill? And how far do you plan to infeed that drill to compensate for the drill point? Just identify some standards here, right? I know what works good for us, 50 thousandths above the part. We're comfortable rapiding into that position and then to begin our infeed. So we use that we've standardized that. Manufacturing guys know it, the estimators know it, and they plan accordingly. And so cycle times become very close to what was estimated. Like I said, again, for blind holes, drill to depth, of course, and then compensate for the drill point. Or perhaps it's a flat bottom, but standardize the method you're going to use of the features that you encounter. When using indexable drills, here again, you need to consider your high pressure constraints, right? Does your machine tool have high pressure? Is the drill capable of it? Do you have, in our case maybe, is there enough ROI there to go after that drill for 10 pieces? Or, should we just simply peck with a high-speed steel or a solid carbide? How do you handle chamfering? I know one thing, all of our holes are chamfered. Absolutely, that's our internal standard, right? 5 max, corner break. Maybe 5 to 10, whatever. So how do you process that? Well, yeah, there's some logic behind that, isn't there? Is it a cam point? Is it a self-centering point drill? In our case, we use a lot of self-centering, 135 degree drills, and so we spot after we drill the hole. The drill simply doesn't need a spot, and we found that it burns the corners off the drill faster if we spot. Some more considerations. Your business model, what is that? Is that prototype or production? Because this may dictate a lot of decisions here. And this was really an area we struggled with for a long time. Is we can't treat prototypes like production, and we can't treat production like prototypes, and so we need two business models, don't we? And let's consider these two business models and thinking about how we manufacture holes, right? If the total tolerance on a prototype hole is less than 5/10, then the operator stops after one pass, does a measurement, and continues with a second pass. You say, why would you do that? Well, some of the parts we manufacture are large parts, right? And the material costs are huge. And we don't want to scrap one piece out if all we had to make was one piece, right? Maybe we planned for enough material for only two pieces. And so we only have one piece of scrap to start with, and we need to make all of our offsets on that piece. Or perhaps, in this case, we need to make those offsets on the same piece, so we begin to just creep up on that diameter. And sure, that looks real ugly on cycle time, but that was what we originally planned for. That was the business we were awarded. The customer knew that. We shared it with them. You know, we're going to take multiple cuts on this thing, and while it's not efficient cycle time-wise, you only ask for one component. Then production, we need to consider that, don't we? We can put some limitations here. If the tolerance is a certain size, right, and maybe less than 5/10, we need to consider how we're going to process and size that hole. And maybe if the tolerance is 0.010 of an inch, we can just go in there and blast a drill through. But as long as we've identified that method, it's clear to everyone, and that's the way we're going to process it. And of course, with any logic, if we find a new method, we'll just update our logic. So what inputs do we need then, right, for hole processing? Well, we need the diameter and its size range limits. We need the depth and the overhang that we need in our tool. We need to know whether it's blind or through, and our logic can simply view any yes or no question as a I/O. On, off, on is blind, off is through, right? The tolerance, yep, we can categorize that into groups, can't we? English or metric, it doesn't matter. From this limit to that limit, this is how we process it. From this limit to that limit, that's how we process it, right? Entry and exit. In intersections, how do you deal with those? Are you drilling it at an angle? Do you need to go after some kind of high-end tool for that? What is acceptable to your customer is in terms of burrs, right? We have some issues there, certainly we do. How do you process those? Identify it, make sure everybody knows. Find a best practice and stick with it. And if it isn't working, correct the process. Another one here, again, going back to our business model. What's the quantity? And then again, what's the material? We certainly need to take material into account on how we process things. And there again, we can categorize them, can't we? That's an industry standard. You can find it on any insert pack. Some more processing logic and size tolerance for axial holes. When the total tolerance is greater than 10 thou and the surface finish is greater or equal to 125, we drill the hole and chamfer it with a spot drill. And that's simply our logic. So then do the spot drill followed by the standard drill, right? No boring or reaming is necessary. And then we look at hole size, okay? If the hole size is 1/8 to 3/8, we're going to go after some standard drill there, right? And we can start to understand through this logic what machine platform is making sense here, right? And so our logic is going to do that for us also. We can say, okay, well, we've started to understand the length to diameters now. Perhaps it's a good Swiss part, or perhaps it's a fixed headstock machine part, or perhaps we're looking at a mill part because all we've told the logic is that we're pocketing holes. Whatever it be. More on processing and logic size here. And you can read through this, folks. I don't need to go through this, but this is what we've identified as best practice. I talked a little bit earlier about standardizing your inventory, your tooling inventory. And certainly this is another burden, and there's a lot of work that goes into this, and perhaps you've adopted this already or you haven't, I don't know. But I say it like this: know what you have, know what you need, and know where to apply it, and know where it's at. So what does this give us? Well, it provides traceability. We can understand the point of use all of a sudden, and that's interesting, isn't it? Perhaps you've departmentalized your shop, and you have these types of machines over here and those types, or perhaps you operate in cells, and you have this cell and you have that cell. Understand which department or which cell uses what tools, and put them in close proximity to those departments. Or maybe you need to consider having duplicates of those tools. Target productivity. Certainly we do that. You guys probably do it better than we do at times. Again, being a prototype shop, productivity isn't the big picture to us. But certainly important in high volume. And so again, you need to consider your business model. Reduce your inventory. That's important, isn't it? Reduce that waste. Another lean principle. And so we've adopted that as standardization, right? And we can do that through the means of some of the quick change technology. But at the end of the day, we need to consider what our ROI is on all these processes. So here's some more ROI considerations. Let's look at coolant through. When do we need coolant through, right? And we just simply say it like this: if we're 8 times diameter in length, we want coolant through, regardless of the material. Certainly we need coolant through on other materials, and we can identify that in the logic. When you plug this material in, if you say hole, buddy, we need coolant through. Maybe it's an exotic alloy, what have you. And so for the logic, we can look something like this. Just simply identify a variable for coolant through, right? And give it a 1 or a 0. Turn it on, turn it off, just like your machine tool does. But you need to consider that as well. Is your machine tool capable of that? And is the machine tool that's best identified for this project capable of that, right? Here again, we can consider business model. How many pieces are we going to run? Can we just muddle through peck drilling with a high-speed steel drill? Or do we actually need that productivity? Or do we actually need that to produce the tolerance that we need, right? And so we can consider things like this just by simple logic and identify the best practice. What's your best practice? And if it doesn't work, adjust it. Here I'll show an inventory chart. We can look at this after the session's over, but I've just identified some of the drills we have in-house, where they're located, what jobs they're for, and so now we have a searchable database. Simple Excel, took a couple of days. Turning logic, that's interesting, huh? What kind of features do we encounter there, and what do we need to know? What does the estimator need to plug in? Well, starting diameter, certainly. What size stock are you cutting down from? What's your final diameter, and so how can we process between the two? How many roughing passes do we need? What can our inserts handle? What kind of feeds and speeds do we need to consider? All that. Total tolerance, certainly. What kind of finishing passes do we need? Surface finish. What kind of feed rate can we encounter? Can we push that tool and get it done and get it over with, or do we need to produce maybe a 16 or 32 finish? And so we can categorize that as well. At this category, we use these feed rates. And we'll just benchmark that on the best practices of the cutting tools, but that demands that somebody stays current with them. Length to turn features, what are we looking at there? What machines make sense? We need our rigidity. How far are we going to hang that bar out on a fixed headstock before we go to a Swiss machine, right? Or does a Swiss machine make sense? What's the OD? What's the limitations there? And how do you machine your shoulders? That's interesting, isn't it? You bring the tool in and drag it up the shoulder, or do you come back around, break the corner, and feed down? Same with the face-off. Do you feed the face-off down, or do you just back drag it all and then come down the face? Identify what your best practice is and stick to it. And if it's not correct, adjust it. So we can look at some of the turning logic here in our calculations, and most of us know all this, right? How to go from RPM to SFM, right? And the equations involved in that. And here they are, and our logic knows how to do that, certainly. It's just a glorified calculator, remember. Yeah, we can compare Okay, so we know we've identified an SFM, say, right? We have a high exotic stainless, and we're only capable of turning it at 210 surface foot. Otherwise, we see thermal cracking on the insert, whatever the issue is. But so we've identified that. Okay. Well, we know our diameter that we're working at. We just input that into the logic, so it can calculate an RPM. And the other thing it can do is it knows the machine tool, so it certainly can calculate and figure out whether that RPM exceeds our maximum RPM on our machine tool. And if it does, we had better back the surface footage down and the feed rate and understand that in the quoting process that we cannot get to that SFM. Now, certainly we're not going to see that in this high alloy example. Perhaps that was a bad example, but brass and aluminum certainly, right? We can run those up in above 1,000 SFM. And if you're talking small diameters, that's a whole lot of RPM. And so you need to consider that. You need to consider what your machine tools are capable of and apply that to your logic if you're gonna take this method, take these means, right? And so all that becomes of this is just simply an identifier to the estimator. Right now, at least in our software, we get an identification, a tag, an earmark, what have you, that, hey, you have an issue here, you need to adjust accordingly. And suppose you could define that as well. You know, here again, what kind of feed rates do you need to have, you know? Well, what's your standard roughing feed rate? Again, what are the inserts capable of? What's your finishing feed rates? And we already talked about that. What's the surface finish requirement and so on. And the logic goes on, doesn't it? And certainly there's a lot of this. There's a lot of considerations that need to be accounted for because there's a whole lot of variability in our industry. And really, isn't that what our industry is just a series of compromises continually? We compromise this for that and this for that. And all of a sudden, we finally found that sweet spot in the machine tool in our processes where, yep, it runs good. We've got good capability there. And so, but how many of you actually identify that and record that and document that? Certainly some of us do in process capability studies, CPKs and so on. But interesting thought though, but here's a means to document your best practices and actually employ it, put it to work for you, just to reduce that labor burden associated with estimating. And so the logic goes on and on and on and on and on, and you say, well, that looks like a lot of upfront work to me. I'm not up for that task, but I can tell you now that the return on investment in all this is not very long at all, and it will transform your shop. Some more on standard features here. We can identify some standard machining processes and define each scenario. Drilled holes, their size, you know, are they tapped, are they compound? OD features, is it threaded, is it grooved, is it orthogonally turned, single point turned, is it formed, what is it? Same with the ID, are you threading, are you grooving, are you face grooving, right? What about milling? Are you pocket milling? Are you milling protrusions? Are you linear milling? What are you doing? Are you milling keyways? Are you engraving letters or some kind of symbol? Are you thread milling? Are you broaching? Are you knurling? What is it that you have to do here? And so you can identify that based on some kind of feature, and we're plugging features in, right? We're plugging features in, and it's telling us how to tolerate those. What about optimal cutting speeds and feeds? Here's something that needs to be considered, right? And certainly we need to continually update this. You don't have to look very far back to see the conflict between machine tool and carbide, and look at how far carbide's come and look at how far the machine tools have come. And so we can say it like this, that optimal cutting speeds and feeds are first based on our material selection, are freely provided by all the tooling manufacturers. Certainly they have some input and they can help you at any time. They can be optimized and benchmarked by real world experience. And that's the key here, folks, is that we want to hear from the machinists, right? We can stick a number and hang our thumb in the wind and say, yep, okay, we run it at this speed and feed and so on. And maybe, but is that the truth? Is that actually what your machinists are doing? And do they understand that? You know, do they understand that the tool is capable of going that fast and that it actually performs better at these speeds and feeds? And as an estimator, do you understand that? And maybe you can educate each other. Have that conversation though with the machinists. And through this, We can understand our constraints, can't we? And we can apply it as logic. Now, in some cultures, this is viewed as intrinsic knowledge, isn't it? As job security, and the machinist wants to cling on to that. That's his job security, isn't it? Certainly, and I'm saying that, yeah, it might take a little bit to get it out of them, but once you get it out of them, document it, document what their best practices are. Have that conversation again. We can look at calculators, and I've put some together in Excel here, basically just some of the calculations we used in our logic. This is free to you guys. If you leave a business card or if you pick mine up and give me an email, I'd be more than happy to provide this to you. Like I say, we've got some SFM, RPM calculations, IPM to IPR, inches per minute, inches per rev calculators, all kinds of good stuff in here. Cubic metal removal rates, some estimators on surface finish, and maybe that's not the most accurate, but it can give us some kind of ballpark figure. So here it is. This is what the industry is based around, isn't it? And like I said, if you guys care to have one of these, just get in contact with me, and I'll be happy to send it to you. And after this slideshow here, we can take a look at it. We need to analyze our machine tool capability, don't we? We need to understand the right product for the right job and its importance in our industry. That's a very, very important topic, and that's what makes or breaks a company, quite frankly. Understanding your profit margins and where that product needs to run. What is the best machine tool for this product? Does it make sense for us? Does it make sense for the next guy? Who can be the most efficient at it? That's what awards you business, having the right machine tool for your customer's product and being the most efficient at it. But we need to consider some things here, like the work envelope, and so we know what the workpiece dimensions are, right? We've plugged those in feature by feature, and so we can, through a process of elimination, more or less, dictate what the best machine tool in our shop is. And you can see that in some of the logic if you read through that later. Horsepower and metal removal rates. Certainly we need to understand that. Here again, it's just another calculation. Let the computer do the calculation. Don't rely on yourself to do it. We need to understand the rigidity of the machine tool, and that's something you might not get a straight answer from, always from the machine tool builders, whoever, and I don't mean that to diss anyone, but they want to sell you a machine tool, right? And you need to understand the rigidity of that machine tool. And I'm here to say that there's no way to understand that like buying one and using it, right? And you get a sense for what works better than others, right? We need to understand length to diameter ratios. Certainly we do. We need to understand the pick-off and sub-working ability. Does it have a sub-spindle in it, right? Can it pick the part off, transfer it, take it over, and finish backside operations, right? Are you trying to get parts off complete? Do you have multiple operations? Do you have multiple machine tools? What is it? What is your best practice to what is your benchmark for any one given feature or a number of features? Here again, does it have the spindle stop capability? Does it have live tooling in it? Can you go after some of that milling and some of those other things that were viewed as secondary operations years ago? How many axes does the machine tool have? Do you have a Y-axis? Do you have a B-axis? Do you have a C-axis? What is it? And certainly you have X and Z, I hope. In your mill tool, same way. What axes do you need to utilize? And here again, we can understand what machine's the best fit. Certainly, we don't want to make commodity parts on our B-axis machine, do we? No, we don't need that fifth axis, and so we're not utilizing that machine tool properly, are we? Here again, we need to know some technical knowns, and you can most certainly acquire this from your machine tool builder. They've got it readily available. A lot of times, just go on the website. So I give an example here of an Akuma Multis, and we looked at some of its specifics, right? It can machine diameters up to 25.5 inches. It can machine lengths up to 59 inches. Here's the axes that travel, that offset, right? And they offset in this manner and this far. And okay, so X is capable of going 27 3/4. And Y is interesting because we don't have a true XY ball screw setup. Do we know the Okuma triangulates off of 2 of them to do straight line linear moves? So we lose some Y-axis the farther we go up in X. So know that at X0 we can get about 11 inches of travel out of this machine, and it's a giant machine, of course. But what are your machine tools? What are the capabilities of your machine tools? You know, how far do their axes travel? What kind of work envelope can you employ in that machine? We can continue here. What's the workpiece spindle maximum? We need to know that, right? We want an identifier if we go over it at any time trying to acquire a certain surface footage. Do you have the power mill capabilities? What's the RPM on those, right? We need to know that as well, especially for micro tools. Those have become more popular with the nanotechnology today, certainly. So we've got some of these 10 thou end mills for engraving, and I tell you what, 6,000 RPM really doesn't get it done too well. You'll be there all day with their feed rate so low to not break that tool, right? So now maybe you need to look at some retrofit, and when does that make sense, and how do you identify the ROI on that? Well, let the logic do it, right? We can identify that. How many features do you make that require that? How many people know that? I would be willing to bet not many, have documented what type of features and how many they make, and so the logic here can provide you a searchable database of those features. And if you had the question about, well, do I need to go after a high frequency spindle of say 90,000 RPM because that's what this tool tells me, does it make sense for my work envelope, right? Does it make sense to the parts that I manufacture? What would it take to justify having that tool? And with this logic, you could simply just dig into it and say, okay, here it populated me a list of tools that would, of tooling that was required for these features that, needed RPM, and just count that identifier. Count that how many times it's identified that you've maxed out the spindle RPM. Maybe you need to go after a different machine tool or a different capability. How many turrets do you have? And do they have live tooling capability on them? And there again, what's the limitations there? How much spindle torque do you have? How much horsepower do you have? We need to understand that, certainly, with some of the bigger work in these hard to cut materials. We max the machine horsepower out. I know we've encountered this a couple times. The machine tool is only capable of doing 100, the ones we have anyway, of 150% of its required load for only 3 minutes, and we found that out the hard way. We were in the cut a lot longer than that on a great big part that we couldn't turn very fast, and so the tool was in cut for a long time, and the spindle loads were high, and the machine died. And so we had to re-engineer, reinvent ourselves, right, and go after a different machine tool, and now we have a new process and a new program that needs to be done, and so we've reinvented twice for one job, and maybe the volumes were low, and that doesn't make a whole lot of sense. Let's try to get it right the first time, right? So here again, what do you consider, and what does that logic look like, right? What's your work envelope? And you can just simply put that in as some kind of macro number and say workpiece length. If it's less than or equal to this, if it's greater than or equal to that. And so you see here just a process of elimination of your machine tool capability, right? We can just start to identify, well, it's not correct for this one, and it's not correct for that one, and it's not correct for this one, and maybe it's not correct for your shop. I don't know. But at least you now have a means to target the work that makes sense for your machine tools and your processes. Here again, regarding the machine tool, is y-axis required? If it is, we can call it a 1. If it's not, we can call it a 0, and the computer understands that real well. That's Boolean logic. Here again, calculate metal removal rates, and take into consideration successive filters as a means of a process of elimination, and so we can understand what machine tool is best utilized. Here again, we can understand what feed rate does to our machine power and the calculations involved with that. You don't need to look much further than the machinist handbook to find a whole lot of literature on this. Same with power consumption, right? Here's some equations for that. And I'm not going to pretend to understand all this, but I can calculate power consumption if you sat me down with a calculator, but I'd much rather rely on our logic to do it for me. And so we've pokey-yoked that process because I'm maybe not the right guy to be calculating some of these equations. Same with econometrics of our machining, right? How long does the tools last? We can calculate this and predict this, and so we can rely on logic to do this, and once the system's built, it's built, and you can use it every day, rather than maybe turning to it only in a pinch or only in a binder. Maybe it was a customer requirement that asked some of these questions, right, and you scrambled to get them done. Well, here you are. You can have them every day. And there we look at the total cost of quality, don't we? And that's what that last slide was all about. But here's a print for us. We look at some of the features here. We've got some OD turning. We need to groove. We need to face. We need to drill, maybe index drill off center. We've got some axial holes to put in, some axial taps, some pocket milling, some cross drilling, some boring, all kinds of features, right? So, well, yeah, that's all it takes. So you need to consider all of these anyways when you quote a part, don't you? So just plug some entry-level stuff and, tell it what diameter, tell it what length, tell it what the hole size is, tell it what thread you're doing, and let the logic calculate what the best practice is there again. So we came down, it boiled down to, well, we need to build some kind of software, don't we? We need to build some software that makes sense to our operations because perhaps we can't find that on the market today. And so we tasked Mikey and some of the professors nearby to put together a user interface for us, right? Some new software. And here it is, you can see it starts out, give me a quote number, give me a customer name, give me a part number, and give me a material type, and we can begin our quoting process. Plan for the correct number of setups. How many did you plan for, right? Maybe you received the order for 1,000 pieces, but it made sense to run 500 at a time for whatever reason, and so you had 2 setups, not 1. Did you plan for that? Here it asks the question, right? We're prepared to answer it. What's your cutoff, bar transfer, bar pull, bump out process cycles, right? Have you considered those when you did your cycle time? And here, with a couple of inputs, we can understand exactly what those are and how many times it needs to be done in one process. Perhaps if you had a long part on a fixed headstock lathe, you needed to do a couple of bar pulls and go back and come into the cut again and continue turning. So plan for that. And here we can look at OD turn features, can't we? See some of the inputs that are required for those. First of all, how many features do you have? What's the sizes, right? Again, what's the starting size? What's the final size? How do we need to approach that? Grooving. How do you handle grooving? Do you have a best practice for that? I certainly learned something from the Sandvik session the other day. I've never plunged groove in that fashion, but I know one thing, I'm going to go home and try it. So here we can build that into our logic. What's the best practice for grooving? What size tools do you have? What have you standardized to? Is it a 031, a 062, and a 098 wide groove? Whatever you have, whatever makes sense in your shop. Understand that for these features, I need to target these sizes, and all of a sudden you can almost predict what tools you need to buy. Milling cycles, how do you deal with those? Do you need to finish the bottom of that pocket? Are you just finishing the walls? What is it you're doing? Here's, give it the inputs, let it calculate, practice, let it calculate cycle time. Produce axial holes, and the sizing of those. We talked a lot about this in detail already, but what's the hole size? What's the tolerance? How do we need to process it? And you can see on some of these, if you look on the left-hand side, it's starting to add up, starting to calculate cycle time for us, and we're just picking operations off the left-hand navigation here, opening up a window, and it's building us a process for this part, feature by feature, and again, these are searchable. Yeah, what else is feature-based in your shops? Certainly our CAM software is, right? I tell it, I need to do some kind of milling operation or some kind of turning operation. And so our CAM software operates in the same way. And perhaps the 2 systems could be interfaced someday. Maybe you could take the variables out of the quoting logic and have it directly input to your CAM software. I don't know. That's something we haven't really explored yet, but it came to mind when looking at what else is feature-based. And C programming, here's an idea. What we've done, certainly we have our CAM software. Other times we don't utilize that so much, but we built some templates. We built templates feature by feature, and it was just a blank program template with all the preparation codes we needed for that kind of feature. And so all we needed from the CAM software then was just some geometry to plug into that template. And you can see here, I give an example of a deep hole repetitive cycle, and just add your geometry here, add your variables here. Certainly program NC programming can be parametric, just like our logic is, right? And so we can understand them in the same terms. What about our quality systems? What about your CMM? That's feature-based, isn't it? How you check a part, how that part's inspected. Right, and here here you can see one of our parts on a CMM layout, and here's all the features of it. So our inspection is also feature-based, isn't it? We need to know the right micrometer to check the right size OD. We need to have a certain set of bore gauges. We need to understand that just like we understand our tooling, don't we? So in final conclusion today, we could say this. A manufacturing plan can be established by a set of rules and logic, and I hope I've done a good job explaining that today. The manufacturing plan can be executed in total respect to those rules and logic, so long as you have that continuous feedback and input. You can hear from the craftsmen. Don't deprive your craftsmen of their craftsmanship. Get their input when you build this. You can reduce the tediousness, the repetitiveness of the quoting process, of whatever it is, of job planning essentially, right, throughout the entire shop. And look at that in total means. You get the big picture because you didn't do the tedious work. You had time to look at all of it, and take into consideration things maybe you wouldn't otherwise. Variability can become the exception, not the rule. Right? Maybe you've encountered a new feature all of a sudden and the logic can't deal with that. Make that the exception, not the rule. As you build this, you acquire more and more features, right? And so variability then in those features, essentially can become nothing. Maybe you've processed everything there is to process out there. You've done every operation. You've done radial turn milling. You've done broaching. You've done slotting. You've done it all, and perhaps you have. Through highly developed logic, full flexibility and automation can be applied here. And that's where I'd like to see the future of this go. Now we've built the logic to automate our shop, right, haven't we? We've understood all the variation involved in what we do, feature by feature, down to every minute detail. And so perhaps we can employ robotics to make some of this. Now that we have logical decision making just on a couple of inputs, we can turn our shop around and automate it. And so now we have a means to do that in low volume as well, don't we? Because we haven't looked at each part as a different entity. We just looked at it as a series of characteristics of, things we do every day, right? We drill holes, we turn diameters. And now that we have logical decision making and job planning, we can automate that. So I thank you folks. You've been a great audience today. I hope you can take something away from this. And I would turn it over to Mikey. He's our mastermind behind this. Mr. Welch from Aztalan Engineering as well, an esteemed colleague of mine. And he'll take your questions if you have any regarding the logic and where we're at today with this process. So, but again, I thank you. Thank you much.
Yeah, no, feel free to ask any questions. I'll try to do my best to answer them. I think Ryan did a pretty good job at giving a pretty solid overview of what we were trying to accomplish with feature-based quoting. Is there any questions that maybe we could answer for you?
Do you guys want to see these calculators I was talking about? Should we look at those? Do that.
I have a question while you're bringing that up. How do you guys tie in the different feature-based components into the actual end quote?
Well, that was actually, I don't know if you guys can hear me well enough. That was actually one of the big values of this project. It was developed over the course of about a year and a half. And the first step was to essentially develop our book of tribal knowledge, if you will, and document all of the logic that we would use to make a part, even a very complex part. And once that logic is documented, it can be referenced by the programmer, and then we can also check that against what's actually happening on the shop floor. So within the feature-based quoting software, there are engineering tables with speeds, feeds, and some of the logic. So the programmer can use those for guidance, and in situations where that logic may not apply, it's documented so we can have a conversation. Well, how come this logic didn't work on this particular job? What can we do to either change our logic, or was this a one-time thing? That this was a kind of an outlier as far as the job goes. But no, the big value is finally having solid documented intrinsic knowledge. If that answers your question at all.
Well, let me try and ask more specifically. So you've got a lower-end machine that just does a 2-axis turning. So the features you're going to create on that part are much simpler than a more complex part, which might require some offset drilling, some more complex operations. So do you tie any of the costing, the final quote, into the different operations that are involved with the particular part that you're quoting?
We do to some extent. The idea of the feature-based quoting software was, as Ryan said, is basically a smart calculator. It generates a cycle time, although the costing and the actual price that we're going to charge the customer is generated in our ERP system. Perhaps in the future it would be nice to see those talk to each other or communicate, but given the resources we had, we couldn't establish anything like that as of yet. Does that make sense?
Yes.
Yes, sir.
To add to that, how would you apply this to a broader spectrum? Say, my shop has got rotary transfer, CNC, hydromat, Acmes. You'd almost need a cost model for every type of application.
Yep.
So you might take me 3 years to develop.
It could, yeah.
No, it certainly could. And, we have a fair variety of machines in our shop as well, and we basically had to take 3 standard machines that we run a fair amount of parts off of, and we say, okay, we're going to establish logic for machining centers, horizontal and vertical, for our twin spindle, twin turret transfer style lathes, and then, of course, for our Swiss machines, our Sugamis. Like you say, we could have spent another couple of years developing logic for the other machines that we have, but for estimating purposes, and that's exactly what this is for, we found that was the best approach.
And if you were to build this, consider the return on investment. How you get what you put into it, essentially, just like anything, and do what makes sense for you. But try to, when you think in those terms, try to figure out where the most labor burden is on your job planning right now, and address that first. Let the computer do the work that it can, and only have minimal human intervention. Yes, sir.
How long did this take?
It was about 1.5 years in development. We actually just went live with it maybe 3 weeks ago. But yeah, no, it was 1.5 years. It was definitely a major effort. I'm certainly not going to deny that at all. But I think the value is definitely there.
How much was inside and how much was outside resources?
We did bring in a third party. We worked with our state's manufacturing extension partnership, as well as with the State University of Wisconsin, and they did a lot of. They helped with coding the logic and developing the software. But of course, the logic for the machine features came internally.
You know what language base it is?
HTML, I believe.
HTML based. Yes, sir.
I have a Swiss calculator that lets me do features individually, or I can say at the same time. And when there's a lot of things out on the market, and when it comes down to, if you don't know the material, and if you don't know the percentage of cuts, you gotta go find the envelope. And all these things, in my mind, fail at those steps. It's good, it's easy to put features in, it's easy to put lengths of cuts in. It comes down to, well, you can only take 50,000, you only take 50% of the envelope. And where most calculators fail is that if you call the guy and say, well, we didn't put that material in, I want 316 stainless, I got to cut a half-inch slot, 14 inches. And they all fail because they say, well, you got to go find a tool and put that in yourself. And if you talk to anybody doing it, they don't want to give it to you. You got to go find a tool, say how much percentage you cut. And a feature base is a feature base. And this thing works simple. It's just take each tool like you're doing. But I like the fact that you have a history base. And it comes down to it, and it adds in and say, I can do these 3 things at the same time because it was a Swiss machine. And I use it now for anything, because it can just take, like, you do these 5 features at the same time, these things, or I don't put them on.
Right.
It has an on-off switch for doing 2 at the same time, and the whole thing is great, except you gotta sit down and bother the programmer, or go find a tool and say, I'll take 50% cut. So those are where I see feature-based stuff is, not that it's hard, it's a great thing to do, but you gotta have that history of the tool life, and tool cuts, and depth of cuts.
Yep,
Otherwise,
and identify all of that, I'd add
that's
too.
where time comes in. It's not the features, it's the,
Yeah.
you did, the program is nice, you fill it out, and if you
Yeah.
have the feature of being able to turn some stuff on, or simultaneously do stuff, because all you need is one program, I don't care what kind of machine are, you can turn them on or off. And just run it by the length of cuts. The problem comes down to figuring the speeds and how much you can do.
Well, and overhangs and rigidity issues, and yeah, absolutely.
Because usually it says, well, you gotta tell me the tool, I don't know the tool, so we don't give you that. That's where the time is. It's the figuring out the cuts and the depth of the cuts.
Yeah, and a lot of this is about understanding what tools you use, and the best practices there, machining techniques, essentially.
Get your history, you already done it, nobody wants to keep track of it. You just cut so many cuts, the tool just, that probably takes a ton of work.
And that, to my point in the beginning, that was the lack of consistency part. We want to be consistent in how we process these features. Yes, sir.
With only doing it for 3 years, you may not know for sure now, but what do you anticipate your savings? Where do you plan on saving? Coding time? So that you know what you're going to be doing?
In that we're being awarded more business because we can turn quotes around faster than most.
So reduce your turnaround.
Reduce our turnaround time, expose us to new markets in doing so.
Let me ask what's your...
Our time right now. Well, we just went live with this thing, but I don't know. What do you say, Mike?
We try to turn quotes around within 24 to 48 hours, or at least that's been the goal. It's been a tough one to achieve, and this is a tool that we're hoping is going to get us a little bit closer. The market's pretty much demanding that we turn quotes around in really no less than 2 days, which can be a pretty Herculean task if you're doing 20 quotes a day. But the big part of this was we could hopefully capture more market share by being the first people with a quote, because we work with customers that oftentimes are very responsive to that. If you're the first person in with a quote, price isn't quite so sensitive. The fact that you responded that fast is what makes you attractive to the customer.
So it's basically turnaround time. You weren't looking at reducing your total quoting time.
Well, this was born into a crisis, and our crisis is that we wanted to target prototype work, but we didn't have the upfront engineering and estimating roles, and so rather than going out and hiring more Mikeys, essentially, we wanted to understand what the computer could provide for us.
You're welcome.
In your coding process, there's time involved with secondaries and material. How do you guys handle that aspect of it? Do you have other people who just quote that, or have you grown those assumptions on the process that you guys can't do internally?
Outside services has been challenging, yeah.
Say that you need
Right.
as well.
As far as material goes, we run a fairly large gamut of materials, from plastics to high alloy steels, and a lot of that we have in a database already. We have a lot of good solid pricing for material, and of course that can change on in quantity and whatnot. But once again, we're trying to provide an estimate. Outside service was definitely a bit more difficult. We did make some effort to try to capture the logic that our platers, our outside service suppliers were using to price their parts, and we couldn't get a lot of as much cooperation out of them as we would have liked to, understandably. So that was difficult. But as far as outside service goes, that's something we still normally need to go out for a quote. Although we have a fair amount of historical data as well that we can reference.
I'll ask back to my question is, can you do the simultaneous if these tools run in?
Yes, you'd process it as one feature typically, or you'd look at, this. It does take some understanding of the machine tool, certainly. But okay, say in the case of the part that I showed with the cross holes on it, there was 12 cross holes on that part. We would process it as 6. because we assume that it's working from both slides, or both turrets. So some of that is in the inputs I'm getting to. Some of it's in the inputs of what what Mikey's going to enter in here. He needs to understand where that overlap is. I don't know that that's necessarily built into the logic in the greatest detail.
It's not a completely automated system. You still have to have some knowledge of your machine tools and some manufacturing knowledge. It's not, there's some estimating softwares where you can basically take a solid model and it'll calculate material removal and apply a rate to it in a pretty much an automated system. This isn't quite that advanced. It does require some intrinsic knowledge by the estimator or whoever's doing the inputs to understand the machine tools and its capabilities to some extent, although a lot of it is still built into the logic as well.
And that's something we continually look to improve upon. Other questions? No? Well, as I mentioned, if any of you would like the copy of our calculators or a copy of this presentation, feel free to send me an email afterwards. My cards are outside. Or if you want to leave yours, feel free. Thank you much.
Thank you, Ryan and Mikey. Appreciate it. If everybody could make sure you fill out your evaluation forms in front of you. We got 15 minutes before the next session. And for those you going over to the show today, get a chance, stop by the PMPA booth over there. They got some information for those of you that are not PMPA members. It's an organization that's been very good for many of us here. So please stop over at the booth and see Monty or anybody attending that. Thank you.